So, hi everyone, can you hear me? So, hi, thanks so much for coming to my talk. As you can see from the screen, I'm the developer advocate in data science at JetBrains. And I've worked as a data scientist for quite some time, but prior to that, I was actually an academic researcher, like many data scientists. And my background is actually psychology and biostatistics. So one of the first lessons that you learn as a researcher is the classic garbage in, garbage out. And unfortunately, you usually learn this the hard way by getting really excited about some result that you found or some model that you've built that ends up being complete garbage. It's an artifact of something that's gone wrong with your data. So in contrast, the introduction that most people get to data in the context of machine learning are these beautiful little toy data sets. And most people who have done any machine learning whatsoever would be familiar with this data set, the iris data set, where you're asked to classify flowers into one of 3 iris species. So if we have a look at the iris data set, you can see how beautifully curated it is and how well each of those 3 flower species separate out. In fact, it's so neat that you don't actually need to build a model to classify which flower belongs to which group. You can actually just create some rules based on eyeballing that graph. Let's contrast this with some real-world data. So I'm sure from looking at it, you can see a lot of issues. And any model that's going to try and use this data is going to struggle to basically work out which points belong to which group. And this is the core of this talk. We need to understand how to spot and remedy issues in real-world data in order to give our models a fighting chance at actually working. So before continuing, I'm going to be using a few concepts pretty heavily in this presentation. I just want to make sure everyone's on the same page. So we're just going to start with some basic definitions. So the first thing that I want to explain is how we refer to different data fields in the context of machine learning. So the fields in our data can be broken up into 2 groups. The first is the target, which is the thing that we're just trying to predict. In the case of the iris data set, what type of iris it is. And the second are the features. This is the information about our target that we use to make those predictions in our model. The next thing I want to explain are the basic model types that we'll be talking about in this presentation. So the first are classification models. This is where we're trying to predict some sort of categorical variable or one of a number of classes or groups. The second are regression models, where the goal is to predict some sort of continuous variable, say price. And then finally, I'm going to talk about the toolkit that we're going to be using to diagnose issues with our data. So the first is summary statistics. Nothing fancy, you'd be familiar with these, things like min, max, mean, deviations. The second is a very powerful type of table called a crosstab. This is where you take 2 categorical variables and you count the number of observations where their levels interact. So you can see in this crosstab where feature 1 and feature 2 both equal 0, they're around 8 million observations. Nothing too fancy here either. And then finally we have graphs. Graphs are, of course, one of the most important tools for making sense of your data. Working out which graph to use in which context is a bit of an art in and of itself. It would make it a whole nother talk, so we're not going to go into it in too much detail. But what I'll be doing is showing a few specific ways you can use graphs in order to find issues in your data. And I hope it sets you up with the mindset that when something's acting a bit weird with your data, if you visualize it, there's a good chance that whatever's going wrong will just pop out. And to make this presentation a little bit more dynamic, rather than just turning it into a research methodology textbook, we're going to play with a toy problem and see how it can be affected by different issues with the data. And this is actually based on a problem that I worked on in my last job. I was working as a lead data scientist in an ad tech company, and actually some of the examples that I've used are things that happen to us. So it goes to show, it doesn't matter how much experience you have, there are pitfalls that can always trip you up. So, our toy problem. Let's say a mobile app wants to sell their ad space. So yes, I used to work in selling that ad space too. I am sorry, I've moved on. So they're working with your company, this ad tech company, and your company runs real-time auctions in order to sell those ads to advertisers. Now, this sounds pretty simple, but we're not just talking about one ad space, of course. We're talking about more than 2 million per second. So because of infrastructure costs, it's not profitable to send out every single ad space to every single advertiser. So what our sales team have been doing is manually blocking the ones that don't really seem profitable. The issue is that there's so many of them and it's always changing, so they can't keep up. This is where we come in. We've been asked to try and build a model to automate this process. So we decided to try and build two models. A model to categorize whether the ad will sell or not, so a classification model, and also to try and predict the price if it does sell, so a regression model. So to get started with our ad space models, we obviously need to grab some data, and this is where all of the problems begin. So when building a machine learning model, it's really rare that you would design and collect a data set specifically for your project. Rather, you'll need to use data that was gathered for some other purpose. And this brings a number of problems, such as you don't really understand where the measurement came from. You don't actually understand what the field is measuring, or your field is a proxy for something that you're actually interested in. So one of the first mistakes you can make when working with data is making unfounded assumptions about what your data is measuring. And to illustrate this, I want to tell a story that I read recently in a paper. So a group of researchers decided that they would create a project called Criminality from Faces. And they claim that they can identify, based on a person's face, whether they're a criminal or not. Now, let's have a look at the data they used to train their model. Here on the left, we have two faces in the non-criminal group. And here on the right, we have a face from the criminal group. Do you notice anything different about these faces? Well, you might have guessed. They managed to train a model which could classify whether a picture was a mugshot, not whether a person was a criminal. So this is, of course, a fundamental mistake. One of the first lessons you learn in research methodology is check for confounders like this, because they can really mess up the relationship between your features and your targets. So in our data, one of the first things that we need to check is whether our fields mean what we think they do. In the case that we don't have a data dictionary or a nice person at the company to explain this, we need to do a bit of investigation for ourselves. So let's say we have this case. We've dug up two features that we think could be useful for our model, country and region. So we're looking at the names, and we don't really know what region means based on the field. It's just a bunch of numbers, but we think maybe it could be broader geographic classifications like North America, Asia, Europe, etc. So if that were true, what we'd expect is our crosstab to look something like what I'm showing on the screen. So we'd expect, USA and Mexico to be in one region. We would expect the Asian countries to be in another region, the European countries in another region, and so forth. However, our actual crosstab looks rather different. In fact, there's no clear relationship between the two fields. I don't know if you can see one. Actually, I set up this example. There is no relationship. So this means we don't actually know what region means. And in that case, it's actually safer not to use it because we don't really know how to interpret what those different levels mean. So this emphasizes the importance of checking your assumptions about what your fields mean, no matter how straightforward those fields seem from their name. And what it means is, you should check things like, do similar fields relate to each other? Do dissimilar fields not relate to each other? And these two ideas are called convergent and divergent validity, respectively. We also need to check whether any of our features might be measuring the same thing as the target. So if you look here at the relationship between one of our potential features, valid ad category, and one of our targets, whether the ad sold, you can see that these two fields have the same value 99% of the time. So if you look at when they both equal 0, 81% of the observations are there. When you look at when they both equal 1, another 18% of the observations are there. So it's only in one of the boxes, 1% of the time, where those two fields do not have the same value. And this should really set off alarm bells because it indicates they're basically measuring the same thing. So when we do a bit of digging, we find out that this field is only populated after the ad is sold. And this means it contains information the model will not have at the time of prediction. So this is a particularly nasty way in which a field may not represent what we assume it does, and this is called data leakage. We're going to come back to this topic later because it's very, very important in machine learning data preparation. Relationships between fields can sometimes be complex. So if you have a look at this scatter plot between a feature and a target, It looks like a random mess of points. It doesn't seem to be a meaningful pattern. And when we fit a line, the statistics agree with us. There's no relationship here. However, what happens when we group this data by a second feature? What we can see is that in class 0, there's a strong negative relationship between feature 1 and the target. And in class 1, there's a strong positive relationship between them. This is called an interaction, where the relationship between a feature and a target only emerges in the presence of a second feature. Due to these interactions between features, you can't necessarily tell which features are going to be useful for your model just by looking at their one-to-one relationship with the target. So what are you going to do? Are you going to look at every single combination of every feature, see how it relates to the target, and then work it out that way? Like, that sounds really tedious, and data scientists are all about automation. So luckily, you don't need to do that. One really straightforward way of assessing whether a feature is going to be useful in your model is called an all but X approach, where you add every feature but one to your model, run the model, get whatever your model metric's going to be, see how it changes, and then repeat that for every possible feature. So you can see here, if we exclude the operating system, the OS, an add request from the model, that has a much bigger impact on the model accuracy than removing something like whether the add request is coming from Mexico. So that means that OS is one of our most important features. This is called multivariate feature selection. It's a really big and complex topic. All but X is just one approach, but what I would suggest is, or what I'd recommend is, take the time to go through and see what methods are offered by your framework or language of choice, because it's really important in terms of setting up your models with the right features. So now that we've discussed problems with what your data is measuring, let's have a look at some ways your data can trick you into thinking your model is performing better than it actually is. So let's start with a fundamental question. How do we assess how a model performs? Well, a naive approach would be take your whole data set, train a bunch of models, and then pick the very best one. The problem with this approach is that every data set has its own idiosyncrasies, and models are really good at learning patterns. They don't just learn the broad patterns between features and targets, they also pick up on all these little patterns in data sets if we let them. This is a phenomenon known as overfitting, and a model can learn, or this is where a model learns patterns in the training data so well it can no longer generalize to new data. So let's have a look at a really extreme example. So let's say we've fitted a model so well that it describes the training data with 0 error. However, when we try to fit this model to a new set of data, maybe we apply it in the real world, we can see that it actually misses most of the points in the fresh data set, meaning that the error is going to be much higher in the real world than in the training data. This is where the famous train-test split comes in. So you've probably heard of this if you've done any sort of machine learning at all. So what we want to do is set aside a portion of the data that the model hasn't seen while training, and we then use this data set as a proxy to assess how well the model is going to perform when we put it into production or put it out into the real world. So the expectation is that model metrics should be roughly the same in the training data and on our test set. So let's look at an example. Let's say that we train test split and we create a model using the train split. So we achieve a very good accuracy on the train set. However, when we apply this model to the test set, the accuracy drops to almost random. So we can see how the test set has allowed us to spot that overfitting to the train set. So let's look at another scenario. This time we created our train and our test sets and everything seems fine. Our model's performing super well. We're able to get similar results on the train and the test sets. And when we, and then let's go ahead and deploy that model into production. This time our accuracy is really bad. What happened here? The issue is that information from the test set has leaked into the train set, meaning that the model's performance is being artificially inflated. This is another form of that data leakage that I mentioned in the previous section. And creating a train test split that doesn't involve data leakage or some other issue is actually quite tricky. So let's have a look at a few different ways that a poorly designed train test split can impact your model performance. So let's go back to our ad space data. Let's say that we created our train test split by just leaving the last 30% of auctions aside for the test set. And let's compare the summary statistics between the two. The first thing that we notice is that auction ID, which should be unique to every single auction, somehow has less unique values than total values in both the train and the test set. When we dig into this, we realize there are actually duplicates in the auction data. So what this means is that the test data set likely contains some of the exact same observations that we trained on. And this allows the model to overfit and then still achieve good performance on the test set by just fitting to the observations it's already seen. The next problem is we have a different number of unique fields in the country field, or unique values. So we can see that the test set contains all 8 levels of this feature, but the train set only contains 6. So this means that the model is only going to be able to learn patterns for the 6 countries that it has access to, meaning that it can't make accurate predictions for the missing 2 countries when it comes to predicting on fresh data. And finally, you can see that the mean of ads sold and the ad price is very different in both the train and the test sets. So from the looks of it, the auctions in the train set seem to be less successful and perhaps have a lower value than the auctions in the test set. So this means that the model may not be able to predict the performance of higher value successful auctions when it sees them in productions. So this illustrates, of course, the need to make sure that your train test split is done very carefully. It needs to yield equally representative samples from your original data set. And it's safest to use methods that are specifically designed to do this, make sure that you're representing both the features and the target equally in each of those data sets. So an example, if you're using Python, is the train test split method from scikit-learn. So let's say that we've solved our issue with having a clean train test split with no data leakage. I'm actually just wondering, is it possible to get the doors closed? There's a little bit of noise coming in and it's quite distracting. Oh, there's no doors. Okay. I'll power on. Okay. So let's say we've solved our problem with having a clean train test split. We don't have any data leakage. So we go ahead and we train a variety of models and we assess each on the test set as we go. So we come up with a model that seems to perform really well on both the train and the test set. So we go ahead and productionize it. This time we're feeling good. However, we yet again have an issue where the performance on the fresh data is lower than either the train or the test set. What happened this time? So the issue is that by using the test set multiple times in order to test out our models, we're actually now overfitting our model to both the train and the test sets. Models are impossible. So we actually should have only used the test set once. Using it multiple times is an improper use of it. So if that's the case, how do we make sure that we're picking the right model and we haven't just got something that overfits to our train set? The first approach is quite simple. What we do is we take our whole data set and then we split it into train and test. We then create a third split from the train set and we call this the validation set. What we can then do is we train multiple models on our train set and we use that validation data in order to assess its true performance in the real world. Once we've come up with that model that we think performs the best on the validation set, we then apply it to our pristine, clean test set. However, you might have kind of thought to yourself, it actually is going to require quite a lot of data in order to create 3 full data sets that are going to be representative. So what do we do if we don't have that? In this case, we can use a method called k-fold cross-validation. How do we do this? So in this case, we take the whole data set again, and again, we split it into train and test sets. However, this time, instead of partitioning off one validation set, we now split our train set into k different folds, hence the name of the technique. We then set aside one of these folds as our validation set, and we train on the other 2. So we train the model on folds 1 and 2, and we test it on fold 3. We then repeat that exercise, training on one fold that's left out each time. So what we end up with for every single model is k different performance metrics because we've trained that model k times. So what do we do with that? We simply average it, and that gives us our validation estimate for how that model is going to perform in the real world. Once we've gone through all of the different models that we want to train, we then can apply that to our pristine test set again, hopefully giving us a good indication of how it's going to perform in the real world. So now we've successfully dodged all of our issues with assessing model performance. We now have an additional set of problems. This is a general collection of issues that data can throw at us in terms of being dirty or having issues with the data quality. So, unsurprisingly, the first thing to look for when checking for dirty data is just checking whether all of the values of your variables seem plausible. So let's say we look at the summary statistics for our app downloads feature, and we see that the minimum number is a negative number. How is that possible? We're dealing with count values here. Well, maybe it is plausible. Sometimes negative numbers are a stand-in for missing values. Sometimes there's just something wrong with the upstream data. So we're going to have to dig into that and try and work out what's happening. Similarly, let's look at the proportions for our country variable. And what we can see is we have a really high number of auctions from Iceland. It's a really small country and we're really not doing much business there. So this also seems implausible. Again, perhaps it's an issue with how the data's been written. Maybe it's an issue with our sample, which we'll get into in the next section. As you can kind of see, checking for implausible values and solving for them, there's no real silver bullet. You have to kind of dig around and actually check what the cause of these implausible or weird values can be. Speaking of missing values, this is of course another major issue that can pollute your data. So certain algorithms won't actually work when you have missing data, and missing data has the potential to cause massive issues for your model's performance if it's missing in a certain way. So of course, we need to check the ways that the data can be missing. So there are 3 different patterns that we should be checking for. Missing data can be missing completely at random. This means that it's truly random. There's no relationship between the missingness and your features and your targets. It can be missing at random. This means it has a relationship with the features, but not the target. And then it can be missing not at random. I don't know why it's called this. It's a very awkward name. But that means that the missingness has a relationship with the target. This is the most serious form of missingness because it can bias the predictions that your model makes. Let's have a look at our ad space data. When we have a look at this pattern of missingness, we can see that the same auctions have missing data for 3 different variables: for operating system, for app category, and app downloads. We do some additional checks and we find out that that missingness fortunately doesn't have a relationship with our target. That means that it's missing at random. This gives us a starting point to investigate why this data is missing and a sense of how it's going to impact our model. When we dig in a little bit further, we find out that these are auctions from apps that simply don't provide us information about that field. That means that when we build our model, if we decide to use these features, we're simply not going to be able to use it to predict for those particular apps. Depending on the importance of the apps and depending on how many auctions we have coming from those apps, that's going to impact the coverage and basically the effectiveness of our model. So again, like with implausible values, there's no one-size-fits-all solution here. You might have to delete your missing observations. You might be able to replace them. You might have to delete the fields, or you might have to throw out your data altogether and not be able to use it. And this is, again, another one where I could do a whole nother talk on it, and it would be another hour. So the next issue that can lead to dirty data is the presence of outliers. So what are outliers? They're simply extreme values in your data, and they can occur for a variety of reasons. This can range from actual issues with the data, mistakes, to real but rare extreme values that need to be accounted for when building your model. So let's have a look at the distribution of our ad price target. We can see a really weird pattern here. On the left-hand side, we can see that most of our prices fall within a certain range, but we have this quite large group of auctions that seem to have a higher price than all of the others. Why is this? When we dig into it, we find out this is a currency conversion issue. So in our case, we can simply correct for this and get rid of those outliers. But what if we couldn't? Why is leaving outliers in your data such a big issue? Well, let's consider what would happen if we tried to make a regression model which predicts ad price using only the app downloads as a feature. So you can see that without the outliers, the regression line fits quite neatly through the observations, and it gives us a pretty good model that describes the data pretty well. However, what happens when we fail to fix those outliers? Well, our regression line does what regression lines do, and it skews quite aggressively in the direction of those outliers. So this gives us a line that doesn't really describe our data properly anymore, and pretty much is going to give us a model that doesn't fit and generalize very well. So how do we detect these outliers? The easiest way is just to visualize them. So you can use box plots, and as I've already mentioned, violin plots for continuous variables. And there are statistical methods such as the Cox or Mahalanobis distances. So these are basically statistics to detect whether your outliers exceed some sort of deviation from the bulk of your observations. And then one final and very important check is just build your model with and without the outliers. So some techniques, as we've already covered, like regression models, are super sensitive to outliers. Others, like tree-based methods, are much more robust. You can also apply certain transformations which reduce the impact of the outliers as well. So the next and most important issue, next and very important issue to discuss is data imbalance. So data imbalance is when you have an uneven distribution in your categorical variables, and it can affect both targets and features. So let's start with targets. In our case, we have an uneven distribution in our ad sold target, where 82% of the time, an auction is not successful, we cannot sell the ad. So let's say we decide to fit a really dumb model, where we always predict that the ad doesn't sell. You're probably going to think, well, this is stupid. This model's not going to perform very well because we're just always predicting the same outcome. Well, that stupid model gets us to 82% accuracy because 82% of the time, it agrees with the outcome that actually happened. So you can probably see how this is an issue with machine learning models. The way that machine learning models work generally is that they try to reduce the error between what they observe and what they predict. When you have one really big class which dominates your target, it can just be lazy and just guess the same outcome a lot of the time and actually reduce that error a lot just by doing this lazy sort of guessing without actually kind of learning the relationship between your features and your target. So what can we do about it? There are two broad approaches. The first is called undersampling. This is basically went too far. This is where you attempt to basically reduce the size of your larger target class by randomly removing rows. So pretty naive approach. It doesn't work very well if the imbalance is too aggressive or your data are too small. The other approach, as I already spoiled, is called oversampling. So this is where you attempt to create more data in your smaller target classes by some sort of method. So the most naive way of doing it is just to simply copy rows. This doesn't give the data anything or the model anything new to learn from, but it at least takes away that cop-out where it can just guess the majority class. There are more sophisticated methods where you can statistically generate more data using what you have already as a seed. Imbalance classes can also be an issue with features. So if we take a look at the distribution of levels within the app category feature, we can see that it's obviously really imbalanced. So most of our auctions are coming from gaming apps, and we have these really small groups at the bottom, which are to do with ceramics or knitting. So this makes it really hard to work with these sort of features because it doesn't really give the model much to learn from when it comes to these small classes. These kind of imbalances also compound if you have multiple features that are categorical and really imbalanced. So let's take a really extreme case, and let's say that we have a combination of all of the rarest levels of all of our categorical variables. So let's say we have auctions from Malta in ceramics apps on Android devices. We have one auction, and this is in a data set with hundreds of millions of observations. how does this affect our model? This is related to a related issue called the curse of dimensionality. It's a little bit of a dramatic name, but there you go. So this is when you have too many features compared to observations. In the worst cases, you can actually have more features than observations. The reason why this is a problem is because models tend to learn patterns. When you only present one example, the model just memorizes what it sees. So let's see what would happen with the example that we just talked about. The model will basically see that in our very one training example, the auction sold for $1.68. So what the model learns is that next time it sees this combination of features, it's going to make this exact prediction. It's just going to regurgitate what it saw in the training data. However, that's not the case, and statistically, it's not likely that that's going to happen again. In our case, the auction did not sell, and so the price is 0. And so what that means is when you have too many of these uniquely identified observations, the model will start to perform much worse because it's starting to overfit to the training data just by memorizing training examples. So a very popular remedy for high-dimensional data is feature engineering. It's really just a fancy way of saying that you need to clean up your features and turn them into something appropriate for your model. So if we revisit this app category variable, what you can see is, hey, wait, we've got a pattern here. All of these really tiny categories belong to a hobbies group. And if we look through all of the other levels, it actually turns out we can see a similar pattern. They seem to belong to subcategories. So we just use a bit of simple string manipulation, and voila, we go from something like 40 messy, imbalanced levels to something like 10 nice, neat ones that are much more balanced. So feature engineering, another very big area in machine learning. This is just a really simple example, and it can be really simple depending on your input data, but it can also be very complex, and the methods are generally quite idiosyncratic for the type of data that you're using. So we've cleaned up our data, and now we need to check whether we've been trapped by the next pitfall. Our data doesn't represent our target group. So to start to understand this, we need to take a step back and explicitly define what our target group is. As much as we'd like them to, models will never be able to represent everything. And we therefore need to strictly define what we want our models to be able to do. To do this, we define our model's population of interest. This is the group that we want our model to apply to. In the ad space example, our population is all real-time auctions for mobile ad space conducted by our company. You can see how careful and explicit that definition is. It explicitly excludes things like web ad space, things not sold by our company, non-auction ad space sales. It's usually not feasible or practical to actually get the whole population of interest, however. In fact, it's not even really necessary most of the time. And this is where samples come in. Samples are designed to be a microcosm of our population of interest. They need to be representative, however, and the representativeness is the tricky bit. If you're not careful, it's really easy to end up with a sample that somehow misses important parts of the population, or the distribution of those features deviate from your population of interest. So these are called data biases, and they can have really problematic implications for how your model performs in the real world. So one example of this is facial recognition apps developed by US tech companies. So you can see here in this diagram, these algorithms generally fail to perform worse on darker skinned females. And this is kind of a massively problematic thing because essentially these are algorithms that are not just being used for things like recognition for opening a phone or opening a computer. In some countries like the US and the UK, they're actually being used for law enforcement purposes. So the companies have not really said why this is the case, but it seems likely that it's just easier to get hold of images of white male faces when building the training sets, and no one really thought to check whether they were actually performing across all facial types. This leads into our first type of data bias, selection bias. So this is where a non-random sampling is done from the population of interest. And this means that the sample doesn't fully represent the population. It might mean that the distribution of the features or target is different to the population of interest, or in the worst case, we might be leaving out big chunks of our population, as potentially happened with those facial recognition apps. And this is much more likely to happen in smaller samples because it's just harder to get hold of data that represents everyone when you don't have a big enough data set. In the ad space sample, let's say that with the data that we have, it looks like the price of ads increases linearly with the number of downloads that an app has. So if we try to extrapolate from this, what we're going to guess is we can get more and more money the more and more downloads that an app has. So great, right? Whoops. Turns out we have a sampling bias. So we somehow left out a bunch of data on really highly downloaded apps. And because we accidentally left these out of our training data, we've missed the true relationship between the number of app downloads and the actual price that we get. It's much more logarithmic than linear. So without knowing this, we would have made an incorrect extrapolation about the relationship between this feature and the target. The final bias that I want to talk about is survivorship bias. This is a form of bias where our sample only includes those observations that made it past some sort of selection process. So to set the scene, let's go back to World War II. And the US were conducting surveys on planes that had made it back to base and trying to see where the damage occurred in order to be able to reinforce them. So what they did is they created this lovely diagram where they plotted out where all of the bullets had hit, and they're like, okay, great. Where the greatest concentration of red is, let's reinforce there. A very clever mathematician called Abraham Wald said, wait a minute, these are the planes that made it back. What about the ones that didn't? So he'd, of course, correctly identified survivorship bias. It would have been pointless to base the reinforcements on these planes because these were the ones that could actually fly after sustaining damage. So let's have a look at an example of survivorship bias in our ad space data. So remember back to the beginning where I said our sales team were trying to help us by blocking ad space that wasn't very profitable. Well, this introduced a survivorship bias into our data. So if we compare the true distribution of price to the distribution from our sample after they had blocked that unprofitable ad space, we can see there's a big difference. The orange line is the distribution of price in our sample, whereas the blue is the true distribution of price. So what we need to do is ask our sales team to turn off all of that filtering, at least for a little while, get that unbiased sample, and then basically be able to create our models to predict properly. So we're on the home stretch. We finally have an unbiased representative sample of data that measures what we want it to measure and is correctly split into training, validation, and test sets, and we've gotten rid of all of those nasty, dirty data pitfalls. Now we need to make sure we don't screw it up by choosing the right model for our data type. So remember back to the beginning when we were discussing the criminality from faces study. I pointed out that the reason that the models seem to predict criminality so accurately is because they were trying to compare mugshots to non-mugshots. So apart from the fact that I think trying to predict criminality from faces in the first place is not the best idea, if those authors had actually understood a little bit about how image recognition algorithms work, they probably wouldn't have made that mistake in the first place. And this is the case with any machine learning algorithm. I don't want to suggest that you need to have a completely deep understanding of how every algorithm works from the ground up in order to be able to use it, but it is wise to at least have an idea of how the relationship between features and targets are being represented by the model in order to be able to diagnose any unexpected behavior. So, for example, linear regression models assume that the relationship between features and targets are, well, they're linear, they're a straight line. However, if we go back to that relationship between app downloads and the ad price, we can see that it's not. And if we try to fit a linear regression model, we can see that this RMSE value, the model error, is quite high. What this is telling us is if we try to fit a straight line between those two values, our prediction is going to be off by an average of 87 cents. So does this mean that we can't use linear regression here? Well, we actually can, but we need to adjust the shape of the line to fit the data. In this case, as we've already discussed, that relationship is logarithmic. So what we can do is just tell the model, please adjust the shape of this line to be logarithmic. It does, and we can see that that model error shoots down to around 7 cents. So just by having a very simple understanding of how that model is trying to fit that relationship and adjusting for it, we can drastically improve our model fit. Another thing that can trip us up at this stage is not using the right model metrics for our data. So let's revisit that example of having an imbalanced target, and let's assume that we didn't correct for it. So let's think about how our model metric might be affected by this. So we fit a model and we work out the number of times that we correctly and incorrectly predicted that the ad space would and wouldn't sell. So you can see here that we have divided up the auctions that actually sold and did not sell, and those that we predicted would sell. So far, we've been happily chugging along using accuracy to measure all of our models. So let's see how we actually calculate that. We can calculate accuracy as all of the correct predictions divided by the total number of observations. So how does it go with this model? Well, we get 82. Not bad, right? Well, maybe not. The problem with accuracy is it tends to hide how well a model is performing for both outcomes. In our case, how well it's predicting that an ad sold and how well it's predicting that an ad did not sell. So this is where alternative measures come in, and I'm going to talk about two called precision and recall. They're very popular. So what's precision? Precision is the proportion of all of the ad spaces we predicted would sell that actually sold. Hey, but in this case, it's 100%. This is looking even better, right? Well, of course, I'm going to hit you with a no. Let's introduce the third measure, recall. This is the proportion of all ad spaces that actually sold, meaning that we accurately predicted would sell. So in this case, it's close to random. And this sort of discrepancy between accuracy and measures like precision and recall is pretty typical in imbalanced data. And it makes accuracy generally a poor choice when you have these sort of target distributions. So what the precision and recall values are telling us is our model has a tendency to underestimate how likely it is that an ad space will sell. So if we're asking it to select automatically ad spaces to send out, it's going to miss around half of them. In our case, we actually want to reduce the number of ad spaces that we send out. Maybe this is a bit too extreme, but in our case, maybe that might be okay. But let's say we were trying to do the opposite. We're trying to maximize the number of auctions that we had. In this case, this model would be performing very, very poorly. So it goes to kind of emphasize that your choice of model metric needs to be made with both your data in mind, but also the goals of your model. Okay, so when I first started getting into machine learning, I had this impression that newer and more complex and shinier models were better. And this was quickly dispelled, and this is such a common assumption that it has its own name, the no free lunch theorem. Different models have been optimized for different data types and different problems. So you can't just throw, say, I don't know, a 175 billion parameter transformer model at any problem and expect the optimal performance. So one very famous example that's been discussed a lot lately is the poor performance that neural nets have with tabular data. Tabular data is sort of what we've been working with, like where you have rows and columns, as opposed to text or images, which is the more kind of classic input for neural nets. So you can see that here in a paper from a couple of months ago. So the authors compared how well a bunch of tree-based models compared to neural nets in terms of predicting tabular data. So what you can see is that on classification problems, the neural nets down the bottom here tended to only get an accuracy between 70 and 80%. The tree-based models, on the other hand, were able to get between 80 to 95% accuracy. And you can see, to a lesser extent, not quite as dramatic, a similar pattern for regression-based problems. So I was curious about this. I was wondering why this is the case, and I started digging through the papers. And it actually seems that researchers are not 100% sure why this is happening. And what it shows is how complex the fit is between a model and a data set. And the best approach is really just to experiment with a variety of models that seem appropriate. And you just start with the simplest baseline possible and work your way up from there. So that's it. Thank you so much for listening. I hope this gives a taster of what to do when your model's not performing as expected and how to kind of deal with pitfalls in messy real-world data. Thanks.